the end. So a little bit about me. As I said, my name is Artem, and I work at Toptal for more than 3 years right now, currently acting as head of analytics. And basically, our main tools at Toptal are like Python and Scala. So Python for less demanding tasks and Scala for more demanding tasks. We won't be talking about Scala today. We just focus on Python and how to get stuff done. So a little bit about Toptal. Basically, it's a freelance platform, and you probably know about Upwork. Do you? Anyone? All right, so at least someone knows. So basically, Upwork is also a freelance platform, but what differentiates us from Upwork and other platforms is basically focus on quality. And quality is on both sides, on the client side and on the talent side. So we make sure that there are no dumb projects from clients who would like to build another Facebook in under a week for $200. And we also make sure that the talent that we have in our network are top-notch, like professionals. So this is basically what we do, and the company is not that big. However, we handle we have a huge operational load, and we can handle it just because our processes that are very efficient. So, and that's basically where the data comes into play. To make sure we make right decisions, we need to use data. And as processes are complex, and data processing is also complex. So how to deal with it? So let's get started. Is anyone familiar with data warehousing? All right, a couple people. So hope this will be educational, at least for the rest. Oh, nearly forgot, guys. So while I'm talking and showing you slides, you could try to open this link. Is it readable? So this is basically the repository that I'll be using during the hands-on part. So feel free to check this out. Clone to your local computer and maybe glance through README. There are a couple steps that you will need to do to actually get the code working on your local machine. So that's the repository, and there are two parts, local part and cloud part. And for the cloud part, if you want to kind of code along, you will need credentials files. So this is something that I will share with you for the time of the conference. Sorry, for the time of my talk here. So let me also put it into the shortener. All right. So second link is the credentials.json that you will need for the cloud part. Good. So let's spend 30 seconds so you can actually paste it into the browser and download everything. Are we done here? Does anyone need some time to download this stuff? All right. I think we're good. So, question number one. So, do you guys have any analytics at work where you need to do data processing, get some? All right. So, and question number two: do you have a data warehouse at the company level, or it's mostly ad hoc stuff that you need to do from time to time to get some numbers? At company level. So you have. All right. Anyone else?
Ad hoc, and we're trying to get to the company level.
Oh, yeah, that's the hardest part, actually. I mean, you can set up the infrastructure, you can set up the tech, but then you need the kind of buy-in from the rest of the company to actually make it work. All right, so I see that someone is trying to reach that point, and the rest, is it ad hoc mostly? All right, for some of you. Okay, so basically, what is a data warehouse? Let's start from the basics to make sure we're all on the same page. So there is a definition from Wikipedia, and if you read it, you will see that there are like main traits of the data warehouse. So information there should be consolidated and consistent. Without this, no one will trust your numbers, your data, and will not use it for like day-to-day decision making. Then they should contain historical data as well as like current data. So, I mean, it's usually we're not interested in what we have now, but rather what we had before and where we are now, so we can see the trend. So that's where historical part is really helpful, especially helpful for data scientists that you may have at work, because if you need to backtest a model or do some like fancy stuff, historical data is very helpful here. And like part number 3, it should be used for decision making. Otherwise, it's just data sitting somewhere. No point in having this. So basically, data warehouse is database that has structure that is convenient for OLAP, like analytical processing, and necessary infrastructure to to support all the processes and data extractions that you need. So, and the question is, like, there are all sorts of solutions for data warehousing available, like Pentaho and Informatica, and I believe Microsoft has SQL Server, data warehouse, and also the cloud warehouse. So the question is, why do we need to build our own solution and not get something already existing? And the answer is rather simple. So this is, I think, a screenshot of the Informatica interface. And you see it's mostly like, visual, drag and drop kind of stuff that you do in the proprietary solution of the vendor. And we just wanted a little bit more flexibility and customization compared to these existing solutions. We also wanted to apply standard engineering practices, like testing. And testing with this kind of stuff is really hard. You cannot just have a CI that will run your unit tests and acceptance tests, this kind of stuff. So testing is a big part here, actually. And actually, it's pretty easy to build your own solution, at least at this point in time, where there are all sorts of services for data processing available for you. So what we will be discussing, basically, this is the main subject. It's how to build a scalable data warehousing solution within a reasonable time. And reasonable time is like, get you up and running in under a week and with reasonable costs, leveraging all the good stuff that is already available for you. So let's talk a little bit about classic data warehousing architecture. And we're talking here about batch processing. Stream is a little bit different story. So, and in regard to classic architecture, just consider that we have several sources of data. It may be your production databases, several of them. It may be Google Analytics, it may be Mixpanel, it may be all sorts of data sources that you need to consolidate and aggregate. Hey guys. So the first part is extraction of this data from various sources. So then the second part is transformation of data and consolidation of this data. So at this point, we have to make sure the data is consistent and the solution is performant enough so you can deliver the results in within a needed time frame. And basically, the next thing is the presentation area. Basically, a database that your data analysts, data scientists, business analysts, however you call it, can use for to do some analysis. And at this stage, it is very important to focus on the structure, the schema of your data. It should be really convenient for this kind of all-app workload. And here the consideration of like dimensional modeling comes into play. It's like, I think it's 30 years old approach to like building proper structure of data in your warehouse. And when you have this presentation area, you just, you plug you connect to it from like Tableau or PopSQL or Looker, whatever BI platform you would like to use. You can use actually like Python notebooks if you're a data scientist to connect to this data source and basically do your job. All right, something. All right. Good. So, and what is the minimal setup that we need to actually build a data warehouse? It's basically a Unix machine with enough storage, CPU, and RAM, Python installed, and PostgreSQL or another relational database that will act as a presentation area. And also some kind of dependency resolution and workflow management for your ETL tasks. And this is, like, there is a tool that is called Luigi that we use to kind of make sense and organize all and kind of sort out all the dependencies between tasks that we have in our ETL. So, what is Luigi? It's a Spotify project. I think it's right now 5 or so years old. And basically, this is a Python module. You can just, do pip install Luigi, and here it is. And this library actually helps you to build complex pipelines of bad jobs. And it will also handle dependency resolution, workflow management, and visualization. There are also lots of like existing packages for Luigi, like Hadoop support, BigQuery support. So it's really nice to work with. So in other words, it's Make on steroids. And we'll see in detail how this works later. So just to cover some basic concepts of Luigi. So Luigi has tasks. Tasks have dependencies and have outputs, which are targets. So it's that simple. If you consider some task, it's basically like a function that takes one or more input and produces an output. And when you specify requirements and outputs, you kind of implicitly define a graph of dependency between different tasks. And Luigi's job is to actually kind of figure out what needs to be run first, what needs to be run second, and so on and so forth. So the power of this thing comes from these facts. Tasks can be parameterized. For instance, you can have like a task parameterized on a date, like getting some statistics on a particular date. And this is very helpful if you want to have like some historical picture of what has happened in your company. Targets can be pretty much anything. It can be local files. It can be tables in PostgreSQL or other relational database. It can be tables in BigQuery. So it's basically any artifact that you can check for existence. And again, lots of stuff already included with Luigi. And this is how our production ETL looks like. It's like lots of tasks, lots of connections between tasks. And well, I mean, this looks like madness, but actually it is really easy to work with and reason about, because single tasks is like a pure function. Several inputs, one output. So you don't have to keep all the context in your head about how things relate to each other. So let's see how it looks in the code. And here, let me switch to the editor. So let's start with the local. So has anyone managed to clone the repository? All right, couple people. So I guess then we'll just do more like a sing-along rather than workshop kind of stuff. So let's take a look at the domain that we'll be working with. So assume that we have a car rental company, daily car, and we have data about our users, about cars that we have in our car park, about rents, basically who rented what car when. And we also have kind of police database with all the fines attributed to each car, like speed limits, improper parking, whatever. And we just want to aggregate this data and get basically attribute each fine to a car and a person who rented this car at some particular point in time. So we can then bug these people later on. So basically, this is the data that we work with. You see, it's very minimal. You can actually play with the generation parameters to get more data or less data, but ignore extension. Yeah, but I mean, the structure is rather simple for our purposes. So cars is, so can you see it, or do I need to? All right, good. So cars look like this. Users look like this, and I was researching what are the most common Romanian names, and hopefully I didn't mess up here. Then we have rents, which is a simple table. It just connects the user with a car and a date on which the car was rented. And we also have another table, which is fines. As you see, it is based on the car reg number, not on car ID, because there is no such a thing in police database as your car ID. So basically, that's the structure that we will be working with. And as I said, the first part of the ETL is always extraction. Let's get the data to some place where we can actually work with it. So, and here we have this extract.py. So basically, what is a Luigi task? As I said, it's rather simple. So you see here that you just define a class. By the way, are you familiar with Python? All right. No, not really. Okay, so some are, some not, but I mean, it's hopefully it's rather readable without this deep understanding of the language. So what we have here is basically a class that inherits from Luigi task that has an output and doesn't have any requirements. And then the run method is something that will be run by Luigi to produce the output. So here, basically, it's very simple. I just want to take a file from sample data generated and write it to our target directory. So as you see, there are 4 tasks: extract users, extract cars, extract rents, and extract fines, which just copy file from cars to some target directory that is specified in the config. So you see here, its target directory is target. So let's run some task. For instance, let's run extract users. Hopefully this will work. All right, it worked. And it actually extracted users successfully. So as you see, a nice touch here. So let's take a look what we have. So if we list target directory, you will see that there is directory 2017 November 15, and this is exactly the date that I specified here with the on parameter. As you see, here we have on, which is a date parameter for Luigi. And you can have many other parameters. You can have date range parameters, so lots of different stuff. So we extracted our file, like our data source, into the target directory. So what will happen if I try to run this task one more time? Any ideas?
It will not work because the output has already been generated.
I mean, it will work, but it will not do anything. It will just check that, all right, there is one present dependency, so we don't need to do anything. Good. So basically, if the artifact or the target is present, we don't want to run the task one more time. So we can also extract finds, and it will do similar thing. First time it runs successfully. Second time, it will say that the dependency is present, so we're good. Basically, this is that simple. We have extraction that is working, and then the next phase is actually about processing this data. So let's take a look at the transform.py. Here we have one task that takes all these that defines all these extract tasks as its dependencies. So we need users, we need cars, rents, and fines to actually get stuff done. And that defines an output, which will be in reachfinds.csv file. And then we have run method, which is just, some pandas code that joins everything and makes sure that we have the right schema at the end. So it's rather simple here. We just rename some columns, we merge all these all these data frames into one final data frame. We define the schema and we write to the output. Basically, that's the final part where we actually produce the result of the task. So let's see what will happen if we actually run this task. The task is called process finds. So you see that previously we ran two tasks, extract finds, extract users. So these dependencies are present, they are not run again. And two more dependencies, extract cars and extract rents, were actually run. So we have these files in the target directory here, you see. Cars, finds, rents, users, everything's here. And also process finds. The task was also run. So let's take a look at the reachfinds.csv file. Good. So maybe it's actually easier to do here. So you see we have the structure that we defined. We have find data, we have rent data, user data, and car data, everything in one place. So this is something that you can then just, connect your Tableau to and see like what is the average fine for a BMW? What is the average fine for, like a Hyundai Solaris? Like you can also do some text processing and figure out like male names versus female names. And if you do it with this data, you will see there is no difference in fines on average. So I assume that men and women are equally good in terms of driving. So let's move on. So basically, if I run this task once again, you will see that, again, everything's good, we're good, data is there. So, and the last piece is to load the data into the database. And here I have PostgreSQL database set up. So then load.py. Basically, this task looks also rather simple. You just specify some connection parameters to connect to Postgres. You say that this is the table that we want to put data into. And that's pretty much everything. There is some boilerplate here, which is for like skipping the header of the CSV. But everything is rather simple. And you see we are inheriting from copy to table. So this stuff is already pre-built into Luigi. You don't have to invent this, which is also nice. Yeah, so let's see. Let's try to actually run this task. It's going to be load reach finds. Okay, let's see what we'll have. All right, you see there's one present dependency that we encountered. Damn, let me try to fix this. I think I already ran it. Okay. Mhm. Right. Good. So let's try to run it once again. Load reach finds. Good. You see that the task one dependency, which is process finds file, which is specified here at the requires section, it was already present, so we're good. And one task was actually run. So let's take a look at the database. Right, and we have everything in Postgres, and pretty much anyone can connect to it via JDBC, direct connection, whatever. So it's that simple. So basically, I think that's what we needed to cover for the first part. And this is the local setup. And the question is, I mean, at least, would I run this in production? Well, and like, the answer is kind of obvious. No, I would not, for several reasons. And one is, it's all on the single machine. So if this machine goes down, you lose all your data. You lose everything, and then you have to explain to your boss, like, well, something has happened, I don't know. So this is not a very good solution. So for peace of mind, I'd rather have more durable storage. Again, like, you can go with like several machines and NFS. It will be a little bit more, a little bit better. I would also go with a proper serialization format. Like CSV is nice, but not perfect, because there are no kind of types there, and you don't have this validation at the end of each task. It's basically like when you work with languages like Scala, you have typed input and typed output, and everything is type checked at the bounds. So you don't have to worry about whether like some task will produce an output that is not consistent with the schema, and then everything will be messed up. So serialization format is nice, and also it would be better to have a scalable OLAP database, because if your people start doing like full scans on your Postgres, the performance will degrade rather soon, and you will either have to invent something to make it run faster, or just, well, better use some existing solution that already solves this problem. So let's start with the storage. And in Google Cloud, there is not much choice. They have just Google Cloud Storage, and this is pretty much what we'll be working with. And the storage is durable, it has very high availability, and it's scalable. So you don't have to worry about losing your data or like scaling access to your data. So this looks good. Then the serialization format. Basically, as I said, garbage in, garbage out. So let's try to reduce, this. Let's try to enforce some constraints on the data, so it's easier to make sense of it. And one good format that you may want to consider is Apache Avro. It relies on schemas, basically where you just specify fields and data types, like fine ID, integer, car registration number, string, or some more complex types. But the schema is embedded into the file, so if you work with like scripting languages, you don't have to. You don't have to kind of have these artifacts from compilation like you would have with other serialization formats. So it's self-contained, so you can just plug it in and start working with it. So this is an example Apache, an example schema in our IDL. So as you see, you just define a record, you define type and the field name. And types can be more complex than just strings. As you see here, we have agenda, which is an enum type. So what is good about Apache Avro? It is convenient to use with dynamic scripting languages. The size is much smaller than the CSV. It's like 5 times smaller than CSV. And it's also supported out of the box in Google Cloud. So again, you don't have to do anything to make it work. it's already set up. So there are other formats, as I said, like one of them would be Parquet, another would be ORC, optimized row columnar, something like this. And essentially the choice is about whether you have your files row-based or column-based. If your data size is not huge, you don't have to worry about this. Just pick arrow and you'll be good. And then the OLAP database. Again, it should be highly available. When your Postgres server goes down, people cannot do their job, and you don't have to worry about this and wake up at night to fix it. So for the peace of mind, highly available database is a good thing to have. It should be scalable. Again, like full scans on Postgres will degrade the performance rather soon. Hopefully, it should be flexible in regard to security and permissions. Like you don't want to, probably, maybe you, not exactly you, but your like CEO probably don't want to have everyone access to like salaries database. So this is something that you may want to secure, and it should be familiar to analysts. Like people don't want to learn new stuff. Well, some people, not you guys. So, we don't want to spend our time on managing OLAP database. I mean, it's something that is not essential to what we're doing. And basically, Google BigQuery is a good solution to this problem. It is highly available. It can scan terabytes of data in seconds. Permission management is somewhat limited, but there are workarounds. And again, it has a good old SQL interface. So no need to learn anything new here. And this is how the web interface looks. Like if you don't want to connect via JDBC or use some other like BI tools, you just go straight to the web interface, you type your query, and you get the result. And you see it's pretty much standard SQL, nothing fancy here. And here I just counted the number of Wikipedia entries with the word data in it. So, and you see it's like 70, around 79,000. Nice. So, basically, if we update our list of data warehousing components, we still have this Unix machine with Python and Luigi. We have cloud storage as distributed, highly available storage, and we have BigQuery as fully managed autoscalable OLAP database. So, let's get to the next part, and let's see how exactly this will look like. What kind of changes we need to make to the processing to make it work on the cloud. So let's first start with the extract task. So you will notice that not many things have changed. Actually, it's just one line. Instead of local target, you write GCS target, and that's pretty much it. It's just all you need is to have a Google Cloud account with credentials, and you're good. So let's take a look, and let's try to run this task and see how it looks like on in Google. So let me go here. I will try to scale this. All right, a little bit too much. Can you see it? I guess not right now. All right, good. So let me just remove this folder. And let's run the task. Local scheduler, and then the module will be cloud, and the task will be extract users. 14. Good. So you see, everything works. Task was run successfully, and if we go to Safari and refresh this, we have the folder and we have the file user CSV inside. So the change was really minimal, and we already have the file in Google Cloud. Similarly for other files. So if you run extract finds, it will also be run. So first time it runs and actually puts the file into the cloud. Second time, Luigi will actually check that the file is present, and it will not run it. So everything's the same, just the location of the target has changed. Good. So then we have the transform part, and this is a little bit different from what we had before, because here I'm not using pandas, but I just wanted to show how you can use Apache Beam to implement this kind of processing pipeline that can be scaled further using Google Cloud Data Flow. So let's take a look. This is a little bit more verbose, but this is something that you have to find your workaround here. So basically, Apache Beam is a library that helps you to define processing pipelines, specify them. And then these pipelines can be run either locally on Apache Spark cluster or using Google Cloud Data Flow, which is a fully managed solution again. So the syntax, again, it's different from pandas, and it's a little bit more verbose, but this is not a showstopper. So if we take a look at the task description, it is still rather readable. So basically here we just read CSV sources for finds, rents, cars, and users. So then we need to enrich our rent data with users and cars. So basically we need to do the join, but because of the way the processing works, and we can imagine that users and cars has much less number of rows than our fines. It's like, we can have millions of fines in the police database, but 100 users and 50 cars. So that's why we can use this like a side input thing in Apache Beam, where you just basically broadcast a small a small data set to the task. So this can be used directly. So let's take a look at this combined with cars and users. So you see that as an input, we have rents data set. It's just a CSV file that we saw before. Then also we have users by ID, and we have cars by ID. It's just simple dictionaries, ID of a user and user row, ID of a car and the car row. So let's take a look at the combined with cars and users. So basically what we do here is we get the corresponding user and car related to the to a particular rent. So you see here user and car, we just take it from the dictionary and we enrich the data. So nothing fancy is happening here. We just put a little bit more information into the row. So this is kind of the map phase of enriching our rents data. So then we need to merge our rents with fines. And here, basically, we know that these rows are related by car registration number and the time when the car was rented and the fine was registered. So basically, we just take our data sets, use these two fields as a key for a particular row, and then just merge on these keys. So we merge on car registration number and the date when the particular car was rented or fine was registered. So this way we get the corresponding rows, and then we can use the flat map transform with the function that is supplied here to get the reach fines, which is exactly the data structure that we need. So basically, for each rent, we have several fines. So basically, we just make a generator here, and we attach fine data into the reach rent data that we have, which is fine ID, fine registered at, and fine amount. So this is a little bit different from pandas. You have to get used to it, but it's actually rather convenient to work with. In Python, it's not that convenient, but if you happen to use Scala, there is a library by Spotify again, who else, which is called Shio. It has a very nice, it's a very nice wrapper around Apache Beam, provides like standard collection interface for this kind of distributed P collections that Apache Beam works with. So again, reach finds, then we extract header, and we write this file to the cloud storage. So there is one additional thing here that is worth mentioning. So let's actually run this task. Good. So we have several dependencies already present. Some warnings, don't mind it. As you see, it's a little bit slower than pandas, but I mean, not a big deal if you have to process like hundreds of gigabytes of data. This is something that you cannot do with pandas, but you can easily do with Apache Beam and like Spark Cluster or Google Cloud Dataflow. Let me see if it's direct runner. All right, so now it's done. So we have two dependencies that were present. Two more dependencies were run. It's extract cards and extract rents, and the process finds task was also successfully finished. So let's take a look how this looks in the Google Cloud Storage. So here you see like the reach finds is not a CSV file anymore, it's a directory. And this directory you have data CSV and the success file. And this happens because when you do distributed data processing, there are multiple workers that process your data. And multiple workers can actually write data to the cloud. So if you have 5 machines, there can be 5 different files here, which combined will give you the whole data set. So that's why we need to present it in the following format. Yeah, so that's basically how you run it directly on your local machine. But if we just change this to Dataflow Runner and remove the target. Oops. Sorry about that. Good. So, and we try to run it once again. It will take much more time to run just because it will go to the Google Cloud. It will try to instantiate some virtual machines that will do the processing for you. It will also scale automatically depending on the amount of data that needs to be processed. So again, you don't have to worry about like how many machines do I need. Like all these considerations are already built into the data flow. So while it's running, let's take a look at how it actually looks in the data flow interface. So as you see, like I already ran this task earlier, probably yesterday, and basically data flow again, it builds the processing pipeline, so you can see all the steps of the pipeline that needs to be executed. This visualization is rather helpful. If something goes wrong, you can understand what stage has failed, so you can debug it and make it work. You also see that like how many workers were used to actually run this task. So in this particular case, it was 1 worker because the data set is tiny. If you have, again, 100 of gigabytes, it will be more workers, maybe 10, 15, it depends. But it is done automatically. That's the best part here. So let's see. Yeah, it's still working. So because it has to instantiate all these virtual machines, it takes more time. But I mean, if the task needs to be run like for 6 hours, this extra 2 minutes will not make a real difference. So that's fine. And what is also good about this, you can actually mix and match. So you can have your Apache Beam tasks run on data flow to make the initial processing, and then you can work with the smaller data sets already pre-aggregated using pandas. And you can actually have best of both worlds here. So there is, as you see, we can plug another task in the cloud using standard pandas interface in the run method, and it will be just fine. So let's see. Yeah, it's still working, but I guess it should be yes. So you see the new task was created here. It shows the pipeline was instantiated. And right now it's trying to figure out the auto-scaling settings for the processing. And it will take, I think, about 3 or 4 minutes to get this done. Yes?
Can we ask questions?
Absolutely.
Okay. So I'm not clear on pandas versus beam.
Right.
Can you help me understand the 3 main differences or 3 major factors that would help me decide between the two of them?
Sure. So I would say that the main factor is the size of your data. Oh, so the question was, how do I decide between pandas and Apache Beam? So, and the answer is, if your data can be fit into a single machine, you will probably be better off with pandas, because it's like it's very well optimized. It has like C code, so it will just process things faster, and it's also just less lines of code. But if your data set cannot be easily fit into a single machine, then there is just no other way. You have to use something like Apache Beam, or if you already have like Spark, you can use PySpark. So just depending on the data set size. And also, what is good about Apache Beam, it actually supports, I mean, it's the same tool if you need to do streaming. So you don't have to switch between like pandas for batch and something else for streaming. You can just use Apache Beam, and it will cover both batch processing and stream processing. So any other questions?
Thank you.
All right, awesome. So yeah, it is run. Again, it will take probably a couple minutes more to finish. Yeah, there is one worker right now, so you can actually check out the logs. So very nice, convenient interface here. And I guess like watching how this is being run is not of our main interest. So let's switch back to the code. Right, and so the last part is loading of data. And here we will just load data into BigQuery. As you see here, it's again not very complicated. There is already a pre-built package for this, which is called BigQuery load task. It will take your data from the Google Cloud Storage. Basically, we specify that all the files under each finds, which has data CSV, will be taken and loaded into BigQuery table. And the BigQuery table is specified here. BigQuery target, we set project ID and dataset ID, and we get rich finds at the end. So let's take a look at BigQuery. Right, so we have the cloud data dataset here and the rich finds table. So there is already some data in this table. This is just because I ran it a little bit earlier. But you see, it's very similar to what we had in Postgres. Same data, same types, and you can connect to it from pretty much any business, any BI tool. And you can actually query this table. For instance, let's just switch to the standard SQL. And here we have rich finds, and let's select some fine amount. And we don't need this limit here. All right. Let's try to run this query. Good. So, and overall it was 75 euros in fines for 10 people. Well, not bad. Looks like speed limits are not honored that much. So that's how it looks, like the full processing pipeline. And the change is rather minimal here. You could actually go with the same extract task instead of Apache Beam task here, just for the sake of illustration how you can do it differently. But again, everything is already pre-built. You just need to set up an account in Google Cloud and you're good to go. So let's proceed. And the next question is, good, but how much does it cost? And actually, it's not that much if you consider the average salary of an engineer who will be working on the infrastructure, like on your own infrastructure. So cloud storage is around $26 per terabyte. So I mean, it's just negligible. BigQuery is $5 per terabyte, and first terabyte is free. So if you're not dealing with, like enormous data sets, like petabytes, the cost is not that high. And the compute engine is $0.94 per hour for this like 16 CPU, 100 gigabytes of RAM machine. So since the ETL is a batch processing and the like virtual machines are spun up and then being shut down, it's actually not that much time spent on this. So you can actually spend like $100 per month if you cook it properly. So costs are very reasonable here. So there is a drawback in regard to BigQuery pricing, and basically this is unpredictable, as it was stated. The cost is dependent on the amount of data scanned, and this is something you cannot control. You just ingest data into BigQuery, and you have no idea how exactly it will be scanned internally. So just pay attention to your current situation during the month to make sure it will not cost you a fortune. So yes.
Keep this cost under control by using some optimizing tips and tricks.
Do you mean in terms of BigQuery?
Yes. Are there any optimizing methods, or it's just unknown and you cannot predict
Well,
execution cost of
as far as I know, there is no way you can optimize something. So you cannot specify indexes, you cannot do any fancy stuff. So
the black box?
Kind of. So just, you may want to specify you may want to specify an alarm in your Google Cloud billing. So when it reaches a certain point, you just try to see what is going on, because maybe someone is going crazy in your company and is doing all sorts of data processing that you just don't need, or maybe he's processing some data for his side job using your BigQuery Google Cloud account. So just make sure you have the monitoring on your costs. But so far we didn't have any issues with the cost of Google Cloud for us. It is way under an average salary of an engineer. So in this regard, it's a good investment. And since you don't have to specify any indexes, and it's just less headache for the engineering team. So yeah, as I said, you load data in BigQuery, and then it just happens. You don't know how exactly. So not all of you are on Google Cloud. So we also have Amazon Web Services, and you can have a similar setup in Amazon, but I have no hands-on experience with it. I can just share my thoughts about this. So Amazon S3 has a similar cost. It's 25 per terabyte of standard storage. Amazon Athena is similar to Google BigQuery, but it works directly on the files in S3. So basically, it has similar querying interface, but there you can actually control. So if you gzip your file in S3, and it will shrink 2 times in size, Athena will consider it 2 times less data to scan. So it will cut down your cost 2 times. If you choose like column-oriented serialization format for your files, and you have lots of this kind of aggregate statistics queries, it will also have to scan less amount of data. So here you can do some optimizations. Right. So compression and the row-based versus column-based is something that you can do in AWS. So in this regard, pricing is more predictable. You can actually do something. But again, it's more to think about. And this is basically the wrap-up. So we discussed how to build a reasonable data warehousing solution. And this is becoming easier and easier these days. Like, I don't know, like 7 years before, you had to set up like a Hadoop cluster to actually get stuff done. Right now, you don't have to. It's already made for you. You just need to, enter your credit card details, and you're good to go. You don't need to spend many years again on this. If you have to set up a Hadoop cluster and you assign some engineer in your team to do this, he will probably just disappear for a month or maybe 2 weeks, depending on the skill. But again, it's very it just takes too much effort to do. And if you're a startup or an SMB and you're not willing to invest that heavily in this because like the output is not clear, you can actually take it really slow, take it easy, and just use the cloud solution, and it will be really like the cost will be low, and the amount of time that you need to set this up and running is, again, like you can do it in under a week, one person, at least to get some ETL running. Of course, when you try to make it company-wide, there are other considerations, not just technical, because then you need to have buy-in from other people in the company. And if you do it properly, there's lots of communication that needs to happen, because like if you have 5 departments, they may have slightly different understanding what is an active client. Slightly different. But since it's slightly different, numbers can be hugely different. It's like, one department calculates metrics, another department calculates metrics, and when they report it to CEO, they report like different numbers, and the question is like, what the hell is happening? And it's always to the engineering team that works on the data warehouse. The question is like, guys, what are you doing here? Like, how can we trust these numbers? And you're like, well, there are details. And this is something that you don't want to explain. Basically, it is very important to get agreement on the understanding of the process, on vocabulary and definitions that people use inside your company. So everyone is on the same page, and there is trust in the data. Otherwise, people will always question it. They will ask, they will pretty much bug you all day long, and you will not be able to do the actual work. You will be just answering questions and questions and questions. So not the fun thing to have. So yeah, when you have the infrastructure, when you have some basic stuff, it is very important to think about the architecture of the data in your warehouse. And here, again, I can recommend just one thing, and this is dimensional modeling. It is like an approach to how to structure your data and how to get clarity on the processes. So pretty much like this is about getting agreement on what we understand as an active client, as a churned client, whatever. And it's both oh, sorry. It's both organizational and technical. So you will have to think about like the structure and also the processes that business operates by. So just check out dimensional modeling if you haven't. There is actually like a book from 30 years ago. It's still relevant. We tried to invent our own stuff. It was not better. So definitely check this out. It's like, you know, first 100 pages has pretty much everything you need. And yeah.
There's also a red book from IBM.
Yes. Yes. So again, feel free to choose any resource, but make sure you have buy-in from all the parties that this is what we will be using, this is how we will be doing our work, this is how we will be doing data analysis in the company. So let's see. Yep. So that was pretty much it. Thanks for your attention.